Thanks for everybody for joining and bearing with us on a couple of technical difficulties. My name's Richard. I'm an engineer at AWS Mobile. Specifically, I work on the if you've heard of them, the Amplify teams and AppSync teams at AWS. Today, I am going to talk a bit about some solutions that we have and how we've solved some problems around adding auth to your apps, as well as handling data, specifically data synchronization, and how these apply to security in your mobile applications as well. I'm going to talk about them a bit generically, and in the proper places where it makes sense, I'll talk a bit about some specific implementations across JavaScript, iOS, Android apps, and how they interact with each other. So the first part of the talk, I'm going to focus more on auth and security in your mobile and web apps and what this means to you. So many of you are probably mobile and web developers. You've probably had some requirements from your clients or your customers that you work online with to do different types of security controls. Some of these things might be simple user registration, some validation of emails, things like that. Other things might get a little bit more complex with topics like MFA, adding CAPTCHAs into your applications, things and so forth. But then usually what we find is concepts start to get pretty complex very quickly, right? Some of these might be familiar with the terms like federation, and this is bringing in concepts like social providers into a single endpoint. Maybe you talk about SSO, or you're trying to bring in enterprise controls like SAML. And as you start to research these things, you get into different industry standards like PXE controls for hash-based key exchange, or Signature version 4 if you're used to using AWS, or more commonly some industry standards like OAuth and OIDC and what these are. And as you start to implement them, it's not just getting the bits and pieces right, but it's also making it kind of enjoyable, or at least reducing friction for your customers using your applications from a UX standpoint and across different platforms. And this starts to get really complex as you start to tie this into how people are going to access data into your applications, right? In many cases, for web apps especially, you'll have public access for parts of your application, and then other parts of your application, once people sign in, they'll get specific features that are available to them. This might be, commenting on a blog post, or it might be, being able to save or download a video, right? And this gets really complex when you start to think about relationships in applications. Like if you imagine modern day social media apps, you might have features with photo sharing, for example, to where you can see your photos and only your friends can see your photos, but other people cannot. And the problem kind of cascades when you look at what is access control, what's anonymous versus guest access, right? How these different roles transition over time. And this will only continue to get more complex as the world continues to add more controls into applications, and as we have different vectors of kind of form factors where people can sign in or do different MFA controls. So to talk through this, what I actually want to do is this talk, I want to break down the specific pieces of what's going on behind the scenes so that you can get a better understanding, and then talk about some of the things that you can use to control your access. So the way I'm going to do this is I'm going to talk about like a simple scenario of where a user wants to actually get into a castle, right? So the castle is where all the resources live. This is how access controls are done. And the first thing that I can do trying to get into this castle is I can store a list of passwords somewhere, right? So imagine this is Alice trying to get into the castle. If you're familiar with the classic Bob and Alice security domain users, and I could write the Alice and all of the other users that have access down on a ledger and have a centralized control. This has pros and cons, right? You have some centralized control, so it's very easy to do some validation. On the other hand, if something happens to this knight that's guarding access, you've got some risks here, right? Just logically taking technology out of the equation. This centralized location could be attacked. It could be downloaded. It could be copied without people's knowledge, and other sorts of spoofing that can happen. So there's a big risk in doing this. Now, on the AWS side, how we store user identities and user directories is basically what we're talking about here. Is we have a service called Cognito that has a couple of pieces, and one specific piece is called user pools. This is the mechanism that we use to store all of these user identities, because ultimately, no matter what, you need some sort of directory that has the attributes of those users, like their first name, last name, phone numbers, and so forth. But you don't necessarily have to save all the passwords like I just was showing, because this does have attack vectors. People could use rainbow tables and other things to break them. So what we do is, inside of Cognito user pools, we vend JWT tokens when a user authenticates successfully. I'll talk a little bit more about that in a few. But we use a protocol called secure remote password, which is a PAKE protocol, right? So this is a password authenticated key exchange protocol. And why this is important is we don't actually send passwords over the network. We use this protocol so that we can store verifiers. And the client actually registers its password when a user signs up. And the way that this is done is just kind of high level on the math behind this is we take large prime integers if you're familiar with a little bit of abstract algebra, we do this over what's known as a group. So we get a generator of that group. We call this a primitive root. And what this means is that we can execute an operation across this entire group and generate all of the elements inside of it. And what we do is we take that user's identity, the password, a short-term salt, and we create this verifier from that primitive root. And by using this, we can construct a protocol back and forth so that as clients are communicating back end with the service, they cannot delineate the password from sniffing network traffic or anything like that. So you have protections that if somebody sees the network traffic somehow and they were able to, let's say, crack SSL, they're not able to get the user's information. But even if they got to somehow were able to crack the storage in the back end, they wouldn't be able to reverse the process from there either, because we're not actually storing passwords. And we do some different things across the platforms, right? You can see we've got some large number of mathematics that's happening here. We use some native binaries on iOS and Android. In React Native, we actually use native bridges because JIT is actually disabled on React Native and iOS. And the compiler actually will use inline caches and things like this for large arrays. So we're able to do this quite efficiently across these platforms. So we've tackled the ways that we protect against storing passwords in the backend. What's another way? Like maybe I don't even want to store the password on the back end, because if I were to go around to every single castle that I have access to, well, now I've got to remember, even though I'm not storing passwords, Alice herself needs to actually start creating passwords on these different sites. And that's hard to remember, right? Even if you have some sort of a password manager. So another mechanism is Alice might have a friend that can vouch for her at all of these different castles, right? And she could just say to the knight, well, this is Bob up here. He knows me. Based on that, can you let me in? And this is effectively what we mean by federation in OAuth. And what I mean by that is Alice, instead of knowing all of these individual passwords at all these places, she just wants to use like her social media account or something. She wants to use her log on with Amazon account or Facebook or her Google account. And we do this federation through user pools as well. So she can sign up with her username and password, or she could sign in with a social provider. And it's all federated through this common identity store. Now, what does this actually mean when we look at the nuts and bolts of this? Let's break this apart in a couple of pieces. So there's two kind of frameworks roughly here is the kind of terminology we like to use here for OAuth. And OAuth is actually solving the problem of how does software A give software B access to some user's data without software B having access to user X's login credentials. And it does this via a redirect process to of granting access by essentially using web technologies. And with this framework in place, we can give Open ID Connect credentials, which is a standardization of the tokens, those JWT tokens I was talking about earlier, to those clients, so that we can know their common identity. We can know the access that they have. These are the differences between the ID and access tokens. And then instead of requiring a user to constantly re-log in over and over again every hour, we can extend this using what's known as a code flow to grant refresh tokens to clients. And that allows them, if they securely store these tokens, to pass them to the endpoint to get new ID and access tokens continually up to a period, whatever you want to control yourself, without forcing that client to log in over and over again. So what exactly does this look like in our system diagram and flow? Well, let's say that Alice wanted to use by having a friend vouch for her, she wanted to use Amazon to grant access to this castle. And what she would do is she would go through a resource server. In this case, the server is going to be Cognito user pools. You would show a login screen, or bypass it directly by passing a URL parameter to that endpoint, specifying the provider, saying, it's Amazon here. It might be Facebook, it might be Google. And that will generate a short-term code, usually for a small ephemeral period of time, in like 30 seconds, sometimes 15 seconds, depending on your security posture. The services control this themselves. And the Alice's client, her web view or her native controller, that's being displayed, I'll talk about that in a second, redirects to that third party. She signs in and gets redirected back to the source. In this case, your OAuth 2 endpoint, in Cognito's case, with the code that came back, as well as the correct credential token from that third party provider. And that third part, and now your centralized location can just respond to you with those JWT tokens. So you have successfully authenticated, improved your identity. Therefore, your federation endpoint can give you credentials. Now, how do you know that this wasn't like spoofed in the middle, right? Because you don't want to just like show web views everywhere to all these clients. And the way that this is done is the major providers here, such as Apple and Google across iOS and Android, according to the OAuth spec, they need trusted user agents to allow this flow to work. Otherwise, they deny you when you publish the App Store. So on iOS, it's SF Safari View Controller is for older versions of iOS. The newer standard that's used and can be scoped down to individual apps for control, like apps on your phone, is AS Web Authentication Session. But these are the trusted user agents that basically Apple on the platform in iOS will show these credentials when you do this redirect process. Custom tabs are what's used on Android. The most common way is Chrome, because that's built into the OS with using custom tabs. And this is the user agent that's trusted there. But there's a few more protections that are put in place as part of the spec to prevent things like people in app stores of maybe decompiling your app and publishing something on your behalf, or trying to intercept the calls if they happen to get in between your federation endpoint or your OAuth server and that third party. So one is by using opaque state that's stored in the client. And this is done by, when you do this redirect, sending a opaque string of characters to the service, sends it back to the client, and you get some validation like, okay, this was what the client generated. It did its request that went through, and the service actually stores this string in. Hey, that's actually what you started this request through in the process on your client. Another way is through a protocol known as PKCE. This is a key exchange that started with native apps and started to become standard in SPAs as they've been adopted, and you want to use the same protections. And what happens is actually the client will create a hash with a random private key that it stores, and it sends this to the service. Service responds with code. After it goes through this OAuth flow that I was talking about earlier, the client actually sends again, instead of the hash, this time it actually sends that private key that it used to seed that hash with the code that the service sent to it. The service calculates this the original hash that was sent along with the code, the key, if the code was valid as well, and does a comparison. If these match, you basically get a successful flow. So this is kind of a two-phase verification on both sides. So there's a lot of protections that are taking place on the client as well as the back end of doing independent validation. And this is how we can prevent people from intercepting our calls and spoofing, because they wouldn't have known the original code and hash that was sent when you started the flow. So I've gone through authentication in my flows here, and I know that either Alice has access because she actually created an account in my user directory and logged in, or I'd had a friend vouch for her. But that's getting past the first part of this problem. We call this authentication, or AuthN, proving who you are. Now let's move on to authorization, or AuthZ. This is what resources do you have access to? Because it's very, very possible that people, they authenticate, but then like something happens on their client. This could be, a hack on native apps with, something that was injected into the client from another third party that they went to potentially, or something, that's broken into the device. This could be a web app that maybe had an exfiltration, or rather an infiltration via some rogue JavaScript. You want to, or somebody could have actually done something like taking tokens off of one machine, or part of the app, and this request, even though they got past authentication, you want to know that the request is still valid, being sent across the network. And to do this, we actually look at each request, and we want to make sure that they're valid, they've been signed. But before we get into this, I want to do a small little signing review. I promise this isn't like an interview request or anything like that, or an interview question. But there's a difference between encryption and signing. So as a little bit of a refresher on how some of this works, encryption is, if you've got a public key, I'm using your public key and I'm running it through some algorithm on some data to write a message that only you can read, right? Because only you have access to your private key. If I want to sign something, what I'm doing is I'm taking this message that I want to send, and I'm using my private key to send the message along with a digital signature. Then you can take this message along with my public key and use that digital signature to validate that it's authentic, no tampered with it while I've sent the message across the network. Now, when we send these our requests to a backend API, and these tokens that I had been granted to my client either through the direct authentication or through the third-party OAuth, what happens is I don't validate credentials every single time. I validate the tokens because they are signed, right? And this has a lot of nice properties that go along with it. Let's talk about how this works and why these properties are nice. So the first is, I talked about those tokens that get vended to clients before, the JWT tokens, the identity token, access token, and refresh token. So these are JWT tokens. Some people call these a JOT. And they're broken apart into 3 pieces, right? So you've got a header, payload, signature, broken apart by periods. The header is the algorithm that's done to do that signature. You can see this is an RSA based signature or signing process that happens. And when you're doing this signing with OAuth, every one of these servers they publish their public key to what's known as a well-known endpoint. So this is using a file format known as JWKS, and it's got the details of this algorithm as well, so that the endpoints can do the signaturation. The payload anybody can look at, right? So again, this is signed; it's not encrypted. So you can open this up with a text editor or something else, and you'll see information in there like the issuer, the audience, the subject, as well as the expiration time, which is very important, right? So the expiration time is how long the signature is valid for, and this is a key thing that many people lose sight of when they're talking about sometimes when it comes to JWT tokens, because they are valid until they expire. Now, certain systems will do things with invalidation ahead of expiration time, but for the most part, this is kind of one of the reasons why people use JWT tokens, because of the scalability behind them. You can do fast signing validation. You don't need to store state in the server. Because if essentially state is being stored in the JWT itself, you're sending that down to the client. And then you have other attributes as well, like the username and groups. And these are really strong pieces of metadata that I'll talk about later a bit more too, when you want to do your fine-grained logic and rules for authorization. And then you have the signature itself. And this is important, everything I'm talking about here, I'm making reference to a few AWS things, but for the most part, these are all industry standard things that you can use in your applications and understand. And they could be with AWS services, or they can be, on your own servers themselves or in your own applications independent. But it's important to know how this works, because when you break this apart, what's actually going to happen is you have two ways of proving valid requests over the network. So the older style way that used to happen, and this was on not just web apps, but you saw this on native apps as well, is especially native apps when you're using like an Android, for example, Chrome custom tabs, right? And even on iOS, you've got, you still got cookies, you're storing stuff. And what used to happen is people would actually store this session information around if the user is authorized, if they've gone through their auth process, and they're now trying to prove they're authorized to a request. Every single time they were doing a request, they would send this, like in a post body here, you can see the URL XYZ, and the service would actually need to deserialize that cookie. It would need to then decode it and validate this against a database somehow. And so that usually is a pretty heavy process, and you've got centralized state here that you now need to look up in a database, and maybe have file system IO or something else, and then do the reverse process, right? It's got to encode this, then serialize it over the network, send it back to the client, just to get a simple hello world going. This has several issues with it. First, the problem is you've got a scalability concern just for raw TPS. Secondly, it's very easy for attackers to try to DDoS your service because of the heavier process you've got. You've got a lot of bottlenecks in this right hand side of the process there on the server for the session flow. Then if you start looking at different technologies when it comes to cookies versus local storage and stuff, all apps need to protect themselves against cross-site scripting, right? No matter if you're talking about authorization flows or not, right? XSS is a common attack vector, especially in web applications. But cookies, for that matter, it's very hard to protect yourself against CSRF attacks, right? So cross-site request forgery, because these many times are social attacks on the users that are using your applications. And by storing this information there, you're also at risk at having things that are outside of your control when people redirect to forums or other things, that they can just sniff the network request that you're pushing through, and they can get access to the user's authorization information. Instead, where the industry has gone, and what makes a lot more sense, is the token based on the right hand side. First of all, these tokens can be stored securely in more appropriate storage, like local storage or session storage, depending on if you want to persist across browser sessions. But they've also got and that kind of allows you to organize if you're doing this. Your protections around making sure that you're not vulnerable for XSS for your entire application, not just for authorization information, but just general application usage. But the other thing that's built into here is now instead of doing all of that, encoding and validation against databases and so forth, you've got a very cryptographically secure and fast process on the right-hand side where the validation on each token is just looking at a signature. And so that's using that public key that your OAuth server publishes to do this validation. And then your servers on the right-hand side can actually cache these signatures so that repeated requests coming from clients can be done over and over again. And you get really nice scalability and protections on the right-hand side while you're still getting this state information in your clients to do their fine-grained authorization. Okay, so another technique that's done, and this is most popular on AWS is HMAC-based authorization. So it's similar to some of the other stuff, but it's got a few more properties to it. And so this is you might have heard of it in the past known as SigV4, but I'll talk about how exactly it's done in AWS in a second. Is hash-based or HMAC-based authorization is just a general term. And what you usually do is you take the user's credentials, and by credentials I mean also short-term credentials, not necessarily username and password. So they're short-term credentials that are given by tokens, and you start to just do repeated hashes based on different dimensions. And those dimensions give you multiple layers of protection based on your service profile, your backend profile. So in the AWS case, when we do this, we actually do it by time, by service, by region. And what this means is you're more resilient to replay attacks. First of all, because you're doing time-based hashing here, but your blast radius is much smaller, right? Because you're instead of just having something like just the service, you've got the time and then the service and the region. So people would actually need to figure out the hashes based on all of these things. The other thing is, since that service itself owns the resource, when it's due, this also feeds into the scalability concepts that I was talking about before, because the service just basically needs to do a Boolean like allow or deny check again if that request should be doing an operation, right? In the case of bearer tokens, they can't, like tokens that we were talking about before, they don't actually own that resource. So when you're doing this extra logic check, it doesn't own the resource, so it needs to do some extra logic to perform these authorization checks on that resource, right? So these HMAC-based authorization techniques have more properties to that give you. This is kind of that cloud native sort of control that gives information. Now, in the case of AWS services, the way that we do this is I talked earlier about Cognito and how it's got a few pieces to it. We use a second part of Cognito. The user pools piece was used for the user identity and user flows and OAuth flows earlier. We use this separate part of Cognito called identity pools that turns those tokens into temporary credentials used for this HMAC signing process. So it gives you actually the token along with a access key and a secret key. And the key here is that these access keys and secret keys are short term. They're only valid for 1 hour, and they can't be used without this token. So these AWS credentials come back to you. And what we do is we create a canonicalization of these credentials to HTTP using this 4-part HMAC process. So we take those credentials, we run that HMAC, using the time, using the service, using the region and stuff. And this then is a signature that's popped into a header for all of your requests, whether it's a GET or a POST or something against any of these different services, right? Then that token that I mentioned that comes back from Cognito, that's got to be sent along with this. And this allows, since it was signed using, your credentials, it's in the service. When the service is doing authorization, we get crypto offload at scale, along with expiration and mathematical certainty of security here, so that you can make secure access to your endpoint. Also gives us a couple of other nice things. The biggest one being that we can apply these security controls to resources in AWS, specifically for things like public and private access on buckets. So, for example, if you were to try to create like a photo sharing app or something else and just, using regular JWT tokens, I mean, you could build that in like a Lambda function, and like for every single user comes in, you start to return like specific URLs that are pointed to them. But another mechanism is by using this HMAC process that we're signing with the individual user identity. So we know the subject, right? The actual identity, which is a UUID for that specific client, and that user that's logged in. We're able to partition access controls inside of just a single key space, so that when people are just having guest access and they haven't gone through authentication, they've just got public access, we can apply a policy just for guest users. But then when people actually do transition states and they've now logged in, we can set an IAM policy that's got variables for the logged in user, right? Rather than specifying each policy for each user directly, we can apply generic policies to all authenticated users, or even groups of users, like logical users in HR editors or things like this. And then it applies to the entire key space. So now Alice can, she can get access to things that are in the public part of the bucket, like a public folder, like maybe there's, it's a photo sharing app, or, a music app sharing records. She can get to those public, albums, but she's also got her private albums that only she can see as well. And these give us really strong controls here. So now I'd like to, and as part of this talk, I want to transition a little bit from the pure security and authorization side into the security and data side of the discussion. And what ends up coming up is these are nice controls of the barrier, and then doing some access controls, but we're building real world apps here, right? And like I mentioned earlier, like you might want some scenarios to where like maybe only my friends can see my photos or stuff like this. And to bring it back to our analogy earlier, what I end up seeing a lot of times is things like, only let someone come in if not just they know someone else, but they come from a specific friendly village, for example, right? Or it might be, they're in this editors group, or it might be that they cascade down, they're only friends of my friend, for example. And if you look at these scenarios and how they end up playing out, they end up actually starting to look like a graph, which makes sense when we're building our applications, right? When you build iOS or Android apps, many times your views are presented in hierarchical graphs. You have navigation controllers. Same thing if it was like a React Native app, you've got stacks that you're popping in and off of when you're navigating. And logically, when it comes, or I should rather say the implementation, what these things end up looking like, and this is where I'll kind of dive into the GraphQL world here in a second, is they end up being nested queries for access controls of how people usually implement these things. And this is kind of how we do it on the AWS side as well. So for example, let's say I need to get to some data, let's say this is a blog post system. I only want to do this if the lookup information in another table matches, friendship, right? So for example, I want to get data if someone is friends with Nadia, right? But the friend here with Nadia is actually going to be, Shaggy. And so when Shaggy is going to access something, all we have to do is do a top level query to see if Shaggy actually has a match here in a friendship table, and if so, I can execute my query here. The way that we do this in the GraphQL world that I'll talk about in a second here is by basically running GraphQL statements in our applications. I'm not going to go too deep into the theory behind GraphQL in this talk. There's plenty of material online for that. But the idea is that we basically attach to the leafs of our graph here. So the leaf here would be friend get data as a query. We attach logical resolver functions to fulfill the requests. And as you look at those things, what I was doing there, you might say to yourself, okay, well, this looks, pretty simple. I could actually write this in multiple different ways. Well, the kind of CRUD flows for some of this, actually, they end up getting quite complex very quickly, right? So, I use that only let people into a castle scenario before, but like, what if I just want to put permission if somebody's like an owner of an object? What about just the group? So people in HR, editor, something like this. What if I only want to allow people to update an item if they've created that item, or delete an item if they've created it, and everybody else has read access, right? This starts to explode pretty quickly. And even if you can build it yourself, it's a very error-prone process, and it's best to kind of trade on prior art that's already available. So again, talking about the theory behind some of this, the way that this is normally modeled inside of your systems is by using an ACM, or access control matrix, and this is a system that was first documented by a computer scientist known as Lamson in the 70s. And the idea is that you actually create a matrix that is the intersection between the identities themselves, whether those are roles or users, and the assets or the resources that they're going to try to access. And based on that intersection, you're able to give specific permissions, like read access or write access, for example. Now, I talked about graphs there and how we model some of this with GraphQL inside of AWS today. And this ends up being these concepts end up being pretty powerful to combine together, because what you can do is you can do data modeling along with your access control rules to give really fine-grained permissions. So, I talked about we use GraphQL here. I'm not going to go into all the details of GraphQL today because I want to focus on data and security a bit more. But this is an example of GraphQL schema definition language, or SDL. So that's everything below at the bottom there with the ID, the title, content owner. So these are types, and you create a type called draft, or maybe it's post or something else. And GraphQL gives us directives, and we actually have an auth directive that we provide for creating these ACMs, and then setting up entire backends that allow you to do those specific rules that I talked about earlier. So you can specify owners of types when they're created. So on your CRUD access, you can give overrides for admins. You can do things specifically on known groups, which could be on specific tokens that come through, and the attributes in those JWT tokens. And this is a really powerful system. And how we do this inside of AWS is using the Amplify framework that I'll dive into now. And this will be a nice transition to the second part of the talk. So Amplify is a client framework, right? So this is for building mobile and web apps for front-end engineers. And instead of knowing all the, like I've been talking here a little bit while about a lot of technical detail, and instead of having to build all of that and understand, and it's important to understand how it all works. But even if you understand, instead of having to build all of that over and over again and build against the implementations, what Amplify allows you to do in your mobile and web apps is give you categories that you can program against using, really use case based interfaces, right? Declarative interfaces on what you're doing. So it's not sign in with Cognito or anything like that. It's just sign in, for example, right? And this allows the implementation to be adapted and swapped over time. And we build all of these best practices into the solution so that you get that institutional knowledge. And it's open source so that you can see all the code, all of it happening. You can contribute if you like, but more importantly, you can see how we're operating in the open and putting all of these standards from the industry in place into your applications so that you can leverage them. Got a few pieces to it. The first is it's got a set of libraries. So this is JavaScript, Android, and iOS libraries. The iOS and Android libraries we first released under preview last November. We actually fully released the 1.0 of these a few weeks ago because they've reached GA level. But the JavaScript library has been out since 2017, and the Android and iOS library is built from the ground up in Swift, Java, and Kotlin. You can program with these. The framework also has UI components. For some of this, is like drop-in auth with just like a one line of code and things like that. And then an entire CLI toolchain for build, test, and deploy, as well as doing code generation that using like that transform I showed you with just a few lines of code, you can build your entire backend and it will create all the configuration that the libraries need so that they can connect at runtime to the backend. There's also some advanced stuff that I'm going to talk about in the second half of this talk when it comes to code generation for doing data synchronization. And the framework has a bunch of these different categories in it. Today I'm focusing heavily on the auth category as well as the data store category I'll get into in the second half of this talk. But it's got some other things like doing analytics, predictions for machine learning and AI, storage for content storage, like with S3 and things like that on the back end. So I'd encourage you to look a little bit more in this over time. But kind of like wrapping up the first half of this talk on the authentication side is the Amplify way of doing a bunch of these things and all of these best practices built in is, standardized configuration, right? So in Amplify, using that CLI toolchain, it's just simply running command amplify add auth, add API, add data store, things like this, giving a very simple declarative API. And you notice tying this to the talk, whether it's JS, Swift, or Android, Java and Kotlin, you can do, simple sign up, sign in. We've got a slight deviation here in the how you're doing OAuth flows, but they operate the exact same way, whether it's federated sign in or the newer style on our native apps with sign in with web UI. You as a developer don't need to think about all of those flows and encoding them and building the proper flows in your application. All of these concerns are built in, even using the techniques like opaque state and Pixie underneath the covers. And then you can model your data as you like with these auth rules and still get that nice, familiar interface in your clients when you're building mobile and web apps. So the last thing before I dive into data, the important thing to take away from these auth things is this is very hard and it's complex. Especially since you're dealing with client apps and this environment's untrusted, right? But it's important to know about how this stuff works underneath the covers. It's important to know the complexity of the ecosystem in the industry in general on some of these things. And I'd recommend when you are building these, you should play it safe with battle hard tested tools and services, whether those are AWS tools or those are some industry tools that use some of these standards that I talked about today, like some of the OAuth flows or the signing and validation flows. Only when you've exhausted all avenues of using those existing tools, if you run up to barriers of using them, should you consider actually trying to hand roll some of these things. Not because you shouldn't try it and learn about it on your own. You should learn about these things. You should know how they work. But it's best to let other people, kind of run through some of the errors and the rough spots early, and to use some battle tested tools in your production apps. Okay. So we've talked a lot about securing your apps and what goes into that. Let's talk about the second half, which is data in your mobile and web apps, right? Because you want to know how some of that stuff works on Auth, but you want to just kind of get past that and get it working with your security profile in place. But really what you're doing is you're building different types of apps for your customers or your clients and your consumers, right? These might be banking apps. These might be news apps. These could be, financial applications. They could be, a new type of social media app, especially, as the world is struggling to connect right now in different ways. These could be new ways that people are sharing information, right? Some of them are going to be real-time things while, all parties are connected. It could be alerts coming to your phone if, an update happened, whether it's, banking alert or a new news story. If somebody, that had, sent out a popular tweet or something else, or it could be a chat from a friend of yours. It could also be that you might be, going to, disconnecting a bit. You're in nature, and you're taking some pictures, and you need to synchronize these, or you're trying to save some information in a personal notebook, or it could even be, answering chat messages that you want to optimistically send offline in an async manner, so that when you reconnect, then your friends will get them. And what's interesting, when we studied these problems from an AWS standpoint, and we looked at the different tools that were out there, the requirements of messaging, or even applications that have real-time requirements or offline requirements, they tend to overlap of functionality. It's just kind of the behavior, for the state of the device that needs to change depending on where you're at. And what we discovered is, this problem space is pretty vast, and people solve these things in different ways. And so what I'm going to talk about today is actually some of the problems with the traditional ways that these are solved, which is, client caches, and it comes down to problems rely around programming models and mental overhead for mobile and web developers. I'm going to discuss some of the issues with concurrency, especially when it comes to conflict resolution, because you can imagine in some of those applications, they might be collaborative apps where people have a large opportunity to step on each other when it comes to data. I talked about with the authentication and authorization story, GraphQL plays a big role there. It can also play a big role in data modeling and data synchronization. And I'll talk about how we've used GraphQL to solve these problems on iOS, Android, and JavaScript-based applications in Amplify with Data Store that came out last year. Okay, so to start with on this, before we dive into some of the technical details, I want to talk about application data in your mental model. So you're building a mobile or web app. What are you really thinking about when it comes to the code itself, like how the UX flows and how consumers use your application? Many times people are creating caches. This might be to speed up the network data, right? Like no matter what you do on the server, you're getting physically closer to the client. It's always going to be faster, right? You're going to have nanoseconds of difference at that point. It might be because you want to store data offline. It might be for many reasons, but your mental model is like, okay, I've got this, this data structure. It could be something flat, it could be something nested, it could be something more complex, but I want to put data into it, so I got this cache, I'm putting, keys and values into it. And then I want to, when I'm interacting with my users of my app, I want to iterate over this and render it somehow. This is a very simple mental model. But what ends up happening in many times when you're doing these things in your programming model as a developer, it doesn't usually play out like that. And what's the reason why? Well, the reason why actually comes back to a concept known as the CAP theorem, that if you've built any back-end systems you might have run across before, and not everybody does usually when they're talking about mobile and web apps, but it comes into play here. This is something you should read about sometime. It's also known as Brewer's theorem, which is a computer scientist at Google. And what it comes down to is if you have a distributed system, you usually have three things at play: the consistency of the data across multiple nodes in your system, the availability of that system in general, and you usually have to choose between these if you want to have a partition or network separation, usually between these different nodes in your system. And client apps are actually the ultimate distributed system, if you think about it, because it's a network partition between the client and the backend. And when it comes to this theorem, like client apps usually don't get a choice, right? They either something's available or it's not, right? Especially depending if they're online or offline, right? They have to have a partition just because of the nature of it being a client and a server. And so let's look at how this plays out and where the different concepts between client and backend apply, and where we can learn lessons and they overlap. So first of all, right, I talked about, network partitions between nodes. Well, as I mentioned, you have a partition between your client and the backend, right? This is the ultimate network partition of sorts. You also have stores, right? So you've got stores that might be logical on the host itself. These also could be separate physical databases of sorts. And what people end up doing as well, for many reasons, it might be for performance reasons, it might be operational reasons, is they front those stores with caches. And this is the liveliness of the data. On clients, though, you don't necessarily have capabilities of separating some of these microservices and so forth. So the cache and the store, and this is kind of where the problem starts for many people in the programming model, they end up blending, they get merged. And we'll dive into this in a second. You also have queues, and this is a nice way of decoupling your system and giving you looser mechanisms between these services to interact with each other rather than direct writes and kind of dependencies between them. Queues also come into play on clients, especially when you're going to not just write data asynchronously over the network, but when you're going to ingest data coming in and you want to sequence it so that it's committed to your store in the proper way. Now let's talk about these stores and these caches, right? These are very different things. Caches, they show up all over computing, right? You're probably familiar with CPU caches and stuff like this. There's negative caches, which are very interesting of storing, your misses. And they're the thing to take in mind, and you've probably you might have heard this phrase before, is that caches are not databases, right? And this is really what we mean by stores versus caches, because stores and databases, like, they've got nice data structures that allow you to do things, right? They've got B trees, hash joins for joining different relationships. They give you these nice structures so that you can have data integrity, sometimes different properties like ACID forth. And without them, you don't have referential integrity. And this means that you are pushing constructs to the developer that they need to start tracking these references and handling things like updates on items when they've got relationships, or making sure that the results of your query in like a view in your UI are representative of the data structure underneath when a change is made, or even things like cascading deletes when you're doing mutations on like a post with its comments and so forth. And especially if you're doing writes that will first represent optimistically locally, but especially if they're offline, if you're just using simple caches to do these updates, you've got another consistency issue that you've got to manage between your client and the backend that will introduce a whole nother layer of issues and consistency in the data for your clients, on top of just your regular application flows. Now, the first version of, if you're not familiar with AWS GraphQL service, which is AWS AppSync, this was released in 2017 as well, and it's still the main engine for data in the Amplify framework. But the first version that we released, and we still support this today, was to leverage some simple caches, mainly the Apollo client cache, that we offer HTTP interceptors, or what are known as Apollo links, for people to plug into. And this is nice for some basic scenarios. And what it did was it actually used this cache, which effectively looks like this image on the right hand side. It's got a reference for it's keyed by the query statements themselves, like listing all posts and stuff like this. And then inside of that reference will be other pointers to individual entity objects, like post number 1, post number 2, and so forth, with the author and the content and stuff. And this is nice if you just want to kind of display some data, and it can be good for some basic use cases. But along with this, many developers, and it's not just for JavaScript-based apps, but iOS and Android and stuff, you want to have state management in your app, and you're going to be changing the state based off of different UI interactions. And so you start mixing concerns here, and you get data integrity issues. You start wanting to update data in the cache so that it's referenced in your UI immediately, and it ends up getting extremely complex very quickly. Here's a basic example of this. So let's say I want to list a bunch of my items here, and I want to run some query different than list post. This time I'm going to list all my items that are for my dog-based app, my pets app. My pets app, actually, I should say. It's not just dogs. And I persist this in my cache. That's just a simple hash map. And I'm filtering on my category. It's the dogs that I want here. And what happens is then in my application view, a user does something and they switch some item. They do an update on some field drilling into it. And for that one item number 2, the category is actually a cat, right? Maybe this was a drawing or something else. But I've bound this to my application view because the way that my data binding happened as a reference to my query was just in the simple cache. It didn't represent, there was no referential integrity. And the developer would need to actually do these updates. And this is what commonly happens in these applications. And it seems like a trivial example, but when you're dealing with multiple entities, and most modern applications have 10, 20, 30, 40 entities that have enums and subtypes and so forth. This problem gets exponential. It actually gets factorial very quickly, and it blows out of control. And your application code is riddled with bugs of trying to keep this up to date. So what you usually see is then the next step is when developers want to kind of have these problems taken care of, especially if they're looking at synchronization between client and the backend, and especially if you're dealing with collaborative applications and clients that are offline or sharing data across multiple users. They look at some different data structures with some of this, which we investigated as well. And some of these are operational transforms or OTs for especially text-based applications. Also commutative or convergent replicated data types. CRDTs gets very popular and stuff. And these are interesting on the academic level, but they've got some considerations, especially if you're building applications that you want to scale to tens or hundreds of thousands of users and clients, right? The first is you usually implement these things with some sort of state, right? Because what you end up wanting is you want some sort of, in your application that you're sharing data, you want some sort of associative properties, right? And by associative, I mean, as the client, I have multiple clients that are interacting with the backend. From a physics perspective, I don't know when state's going to, when a request's going to hit the backend from one client versus another. So the order shouldn't matter there. That's why we need associativity properties. And with things like CRDTs, especially, you need to store some state in a location, right? You need all of those actors in the system. Actors are clients here sending their information. And to do this, if you're storing this actor information, you need a garbage collection. Otherwise, your individual writes start to explode. You get something known as sibling explosion. And when you're making these updates, you need the system to be correct, and you need to know when a mutation like a delete is stable. And when to define this, like a delete is stable when all clients have actually recognized, oh, this item's deleted, I can remove this, it shouldn't show up in my UI, right? And when clients are offline for a significant amount of time, a delete becoming stable is a really hard problem to solve. So instead of storing all of this, you need these systems that store all of this and do these actors tracking of them. They become impractical, right? The other thing is when you tie this back to the beginning part of this talk today, with these other systems, you don't really have centralized authority. This makes problems like AuthN and AuthZ really hard to solve. It makes debugging really hard to solve, security and logging and tracing. It makes user intent on an update hard to solve because you kind of lost text through the system when it was replicated. And clearly, if we're talking about storing state for every single write that happens in your system, scaling when you have all of these clients becomes really, really difficult, right? So instead of doing some of this, like you need a centralized authority to do merging of operations in a predictable manner, right? And then once you're doing this merging of operations in a predictable manner, you don't really have this problem of trying to track all the individual updates and merging them across all the clients for storing the actor information. You only need to know that actor information at the time of the request when it came through. And I'll talk about how we do this in Amplify in a moment. The last thing here that you should know about is when you've got these applications and the problem that you want to solve, and this is a generic problem, by the way, this is a Lambda architecture I'm showing here, not anything to do with AWS Lambda, but just the general problem of, effectively a slow or batch layer, which could be, lossy networks or clients that are completely offline, along with a real-time and speed layer. You need to somehow merge these operations and union the results in a predictable manner. And there's this is a common pattern that you usually do on clients with some sort of union or merge operation. And this gets kind of tough when you're talking about mobile and web apps. And in some ways, the problem that you would see there with that was an architecture I showed for big data systems. The problem actually compounds itself on mobile and web apps when you're talking about querying data to get the latest information, especially around synchronization, writes that are offline. And then the client comes back online, you want to reconcile them. And when clients do come back online, they're clearly going to connect to a backend and get some real-time information when we're talking about WebSockets or anything else. And so you basically need some sort of three-way merge process that happens. Let's talk about like what happens here, just the problem. Let's say if we reduce it to a simpler use case with no mutations, right? Just to kind of show this in action. If I have a client that's offline and it comes back online and it needs to get its latest data and results from your backend, and this is true whether you're using AWS Amplify for this, or if you're just like building your own system with like a cache, for example. I want to load some data and it starts to transfer at a specific time and then it finishes later time at TN. In between that time, if a real-time mutation has come in, you're going to have a write to your system. And this is where you need some sort of queuing mechanism that you introduce. Like I talked about originally, taking some of the properties from your backend systems and applying those same concepts with queues to your client. Otherwise, you're going to end up with some data inconsistency, right? You've gotten some updates, the latest information that came from your real-time channel, your query and your fetch finishes. Now you overwrite that in your cache. You're going to have a bunch of messy information. So this is where the solution that we build to solve a bunch of these problems, Amplified Data Store, comes in. So it's multi-platform, like I talked about earlier, similar just like the rest of the Amplify framework. And it comes down to a few key points. The first is it does this versioning of your items. So instead of using some of those data structures like OTs or CRDTs, we actually use effectively what we call a loose versioning over all of the objects. And the service actually controls this. So we have centralized authority so that it can do things like merge operations, conflict resolution. And then we give you different controls over this. Some of it's automatic controls that I'll talk about. Other things are controls that you can do like Lambda functions, for example. But the biggest thing here is we've actually tried to tackle is this programming model. So instead of you having to update different caches and reconcile these to your application views, we give you what we call a local first programming model that you can just do simple save and query and then observe models in your system. And it's much more simpler for you as the developer to rationalize around. And then synchronization takes place automatically in the backend. And that synchronization could be things using stuff like Delta Sync or auto merge, which are mechanisms that we use for offline to online transitions. Or it could be real-time synchronization while the device is online, and we use WebSockets behind the scenes to do this. And all of this is through a centralized authority that's powered by GraphQL using AWS AppSync behind the scenes. But it's just GraphQL compliant. Ultimately, that's the protocol that we leveraged because we wanted a consistent open manner of doing this. So how do we do this? Well, we have a high level architecture here that I'll dive into the individual pieces. And what happens is a developer programs against this simple API that I'll show in the next couple of screens, and the system actually turns these calls. They program using instances of their entities. We call these models. And from that API, the developer can do CRUD operations, including complex queries with conditionals, and they can observe changes to the entities themselves. Now, these changes might happen from an internal action, such as the developer through the user doing some things, or it could be from synchronization process that happens over the network via the storage engine and the sync engine. And that sync engine is what allows us to do some of these operations against the backend using GraphQL. So it will automatically do queries at a regular time for different sync operations, as well as when the client comes back online. It will subscribe to data as it's coming in. It will do this in queuing process. And then the data is persisted locally on the device, depending on the platform. So this would be using SQLite on iOS and Android, using async storage on React Native, using IndexedDB on JavaScript. But then the important thing to take away from here is I'm not showing a different architecture for different platforms. It's the same programming construct across different platforms. So you get a consistent view of how your developers program. You also get a consistent way of data modeling cross-program as well by using GraphQL. So for example, here's how a developer would work. They would do some data modeling on an entity. You would annotate this with an app model here. So let's say they created a post with name, content, and a rating, and they run a build phase. Now, this build phase is different for your platforms. It could be, an NPX script in the JS world, Gradle task in Android Studio. We actually have extensions that you can run and build in. We also have an Xcode build phase that you can, run one command and add it in there. And this is nice because it's actually in your DX flows. I just, build from my IDE. And underneath the covers, we create these models in the target language of choice, in the target platform, right? So these might be TypeScript classes in JS. They will be Swift classes with extensions and some extra metadata in the iOS world. They will be Java classes underneath the covers is how we implement this with some step builders and things like that for building instances in Java or Kotlin. But the developer doesn't need to know about that. All that they do is program against this API. So, for example, here's a JavaScript example. Developer is just creating like a new instance of a post. Hello world, welcome to data store. Put in a rating of 5, and they save. That's it. All of that stuff before I was talking about caches, updating, and relationships. If these were comments on a post and stuff like that, they don't have to worry about that. If they want to run a query, they can just run a simple query to get back all information, or they can give it a conditional here, like give me just the items that have a rating greater than 2. And this is all persisted. The queries actually happen against their local storage engine. So they get that really, really snappy and fast interaction. Now, as I mentioned earlier, all the syncing, whether it's between online and offline or while they're offline using real-time subscriptions, is happening in the back end. So they can observe their model as well. And this is using observables, RX extensions there in Android world, for example, combine in the Swift or in the iOS world. And as data gets updated in your centralized authority in the cloud backend, it's also pushed appropriately to the clients. So anything that they're doing, even though their queries execute locally, they're still getting those real-time results. So their entities and their models start getting updated and represented appropriately in the client side as well. So you get the best of both worlds. And, again, this is very simple. That was a JavaScript example, but this applies across multiple platforms. So here's an example of Kotlin here on Android. I'm going to use a step builder here to create an instance of my post and just do a data store.save. I can do a query. Again, we're getting where my post rating is greater than 4. And then I can simply observe data as well. I'm showing just observing the incoming items, but I could see when the observable started if I wanted to, or when it canceled or errored out on my client as well. So you get that same nice programming model across your different platforms. So that fluent interface is pretty nice, especially when you're using queries, and you can use that query that interface for those criteria on updates. So data store.save as well. And this is pretty nice because if you are building conditions into your application, like I have an account balance that I only want to save on the back end if something is less than something else, if A is greater than B or something. What actually happens is, first of all, since we're doing this code gen in this build phase, your operations are more natural as you're doing programming. So your where clauses effectively are against the fields themselves. The filtering happens locally when you're applying queries, but when you're doing updates, especially when you're offline, what we do is we take that predicate and we apply it in that offline queue. Then when your device comes back online and we send the mutation via GraphQL over the network, we actually use DynamoDB as the backing data store that AppSync interfaces with, and it applies this predicate to the mutation to the write that happens. So if something had changed in the backend, let's say a bank balance was overdrawn or something else, this condition will be applied to that data store. And if it's not valid, then your write isn't going to succeed. And what happens is the client then gets a callback to the service, and you're able to execute your local callback to do something like your write transaction has failed there. So again, you get the best of two worlds here. You can have the optimistic update, especially if you're offline, things like this, the developer can program against. But if the ultimate commit against the network, wasn't successful in that logic happened at the server, it comes back to the client for them to operate appropriately. Okay, so let's dive a bit more into the implementations here and see how this works. So I mentioned the developer there, they model their data, they do this build phase, and now they start programming against instances. What we do is these instances at runtime, they get converted into what we call a model repository inside the storage engine. Happens a few different ways, TypeScript generics, Swift, we use some runtime metadata. We use reflection on the Android side to actually get the type information and store all this information. And then we have an adapter. It's a classic repository with an adapter pattern here in the storage adapter that lets you write to the correct persistent storage medium. Interesting here, what I want to call out on this phase is no AWS account is needed to do this. So if you just like this programming interface and you want to leverage this in your mobile and web apps just as a simpler interface for you to program with offline or locally, you can do this. You don't need to synchronize with the cloud at all. Now, if you choose to sync with the cloud, and the way that you do this in the Amplify side is you would just run an Amplify push there. What we do is, first of all, if you don't have a backend, we create an AppSync backend, DynamoDB tables, resolver function, the authorization modes, everything else for you. And then the client actually starts syncing. So there's a couple of synchronization processes. There's a base sync and a delta sync. So the first way is like if you were doing offline writes, those writes will start to go through the system. So if they were new items, it's going to flow together pretty seamlessly, right? Because there's no conflicts. It's a brand new item on the client. But any existing information is going to be pulled down with a base sync. And so this is a base sync is the initial hydration process. And there's also, it happens on a periodic basis too, which you can control. The default is every 24 hours. And what happens is the results come back from the network in a GraphQL statement. The sync engine actually does the transformation. So it will serialize these network requests to the model repository in the storage engine. Now, you as a developer, if you were observing on these models, or if you just ran a data store.query, the results of those network requests will come back through the data store API. Similarly, it will set up subscriptions using GraphQL for all of your different entities. And any of those that get updated will also go through this serialization process. And the results flow two ways. Now, another interesting thing to know is you can operate on this same backend API across your iOS and Android process, or your iOS, Android, and JavaScript clients. So you can share this backend as you need to do. And so, for example, in a provisioning workflow, you do that, model data modeling with entities with GraphQL types. You'll do save with your data store API and everything else, and do an amplify push, like I mentioned before. Now, when we do this, we actually store this SDL, the schema definition language that you've modeled in the Amplify console as metadata. It just corresponds to your app ID. Then from other developer workstations, like if you popped over to an iOS or Android workstation, they just do an Amplify pull and they run that build phase again. That could be that Xcode build phase or that Gradle task. And it will take that schema and generate the proper models on the client, like your Swift or Java classes. And then it can do its same operations, syncs, data store.save, observes, and it's all going to be shared across this common backend. Okay, so let's talk about the last piece of this talk. Let's talk about what's happening here in the service side here, especially on the sync processes, like I mentioned, base sync and delta sync. But I want to talk about the conflict resolution first as well. So GraphQL is actually what's powering Amplify Data Store. And the service we use here is AppSync to do this, but it's a GraphQL compliant service, right? So open standard here. And in AppSync, what we're doing is actually we create these what are known as sync-enabled resolvers. And I mentioned earlier in the talk, resolvers in GraphQL are the functions that are used to perform operations like writing data or reading data and so forth. But these resolvers, they've got a few things. First of all is on the query side, when you're going to run this base sync, it actually has an operation that's called sync along with the last sync time. And this is what tells the client or tells the backend based on when the client has gone online or offline, if it should return base sync information from like a base table or delta information from between when the client was last offline or not. And I'm going to show a diagram of this in a second. The other thing that it has is on writes for the data store settings is it's got versioned data sources with conflict detection and conflict resolution. And this does a couple of things. It will apply loose versions to each object as they come in. So it does this by using monotonically increasing counters in the service so that it knows the different clients when they were online or offline, and it will check against the last committed write to your DynamoDB database to know if you've drifted or not. And then based on the detection of this, you have different conflict resolution strategies. So this could be a form of optimistic concurrency control. This could be a custom Lambda function that you could use, like only allow writes if the user identity is Jeff the admin or something else. Also, we can use GraphQL to do a pretty cool thing known as auto merge and apply some heuristics to the process so that we can make intelligent choices on behalf of the user if you don't want to actually drill down to that level. I'll talk about this in a second. So these sync-enabled resolvers, they, like I talked about, they do the hydration, they do the delta changes, and you can also filter, on subsets of your data with this as well. And we're actually working on some enhancements to the Amplify Data Store here, the client side in the next couple of months that will allow you to pass some filters from your client as well, so that you can do per user fine-grained filtering here that gets passed to the backend when it does this. But what's important here is when these sync-enabled resolvers return data, your client is actually going to do a few things. So it's going to do that three-way merge that I talked about earlier. It's going to, if you've got offline writes and it comes back online, it's going to, first get the latest data from the back end. It's going to then do some reconciliation of your mutations. Maybe you were trying to mutate data that was against that back end and, needs to know about this, whether it tried to do a write and needs to fire a call back to the client for the developer or the user to do something. And then it's also going to, set up subscriptions first when it's coming back online so that you're not missing any data, but it's only going to apply those subscription results after the sync process is finished for queries and mutation alignment with the latest data on the back end. So you're going to get consistent date there on the client. But I mentioned there's a delta sync process that happens here, right? Because even if you've got a high performance Android and iOS native application, you don't always want to run large queries when you're coming online to offline, right? You just want to get the change results. And this is important even with, fast apps that are running at 60 FPF, because you might get some flickering or some lag in your UX for large data sets, even moderate data sets, to be honest with you, from what we've seen in production. And this is just a result of modern phones and CPUs that are very intensive if you want to do some filtering, and also this is on top of just the error-prone processes that I talked about earlier. So here's how we do this between the client and the backend. I talked about the sync enable resolvers, and I showed you that field of the last sync time before. And so what actually happens is let's go through the write and then the sync and the read flow. So from one client, I'm going to create an item. So I've got create post here, new post Nadia, title hello world. And the sync enable resolver, it actually has two tables in the backend, two DynamoDB tables. The first is the base table. That's your ultimate source of truth that it's writing information. Pretty straightforward. Creates the ID, the fields and the records, and they go in there over time. Then in the Delta table, it creates what are known as time buckets. And the time buckets are created using a combination of the entity type, the current date, the version itself on the item, right, using these monotonically increasing counters I was talking about. And it stores a server-generated timestamp for the last changed app. So rather than storing client timestamps, we do this on the service side to account for client clock drift and things like this, as well as a TTL that you can control as a developer. And the reason it does this is because the normal sync process runs that if I wanted to do a base table fetch, right, either on my initial hydration or my periodic catch-up time as like a sweeper, it's going to just run this sync-enabled resolver, but not pass in any last changed at time. So because it doesn't have this parameter from the client, the resolver on the back end knows that it's going to go over this base table and return the information to the client, including information like the server generated time of the last changed at. So the server generates this time, passes it to client can persist this. It also knows about items that are deleted and the latest versions. So again, that's centralized authority that's sending the information back down to the client so that it's got strong eventual consistency. Now, when the clients, though, in between this base table periodic sweeper, as they're coming between offline and online, as they want to, just get their data that's changed, they've got that last sync time that they got from the server. And they send, again, the exact same query that happened before through this transition process of the sync engine. But now the sync engine is just using that time that it persisted before, of the last sync time. The server uses a DynamoDB query, a specific query, not a scan or anything, and it looks inside this time bucket, gives the client just the items that changed in that period, and the client then uses this to update their local store. Now, the TTL is interesting here on the Delta table, because this effectively becomes a change journal of sorts. And on the back end, we use DynamoDB TTLs here with this field to evict the old items as they roll over time. So this gives us really nice optimization and performance on this change log in this journal as you're using it in a production application. Okay, so now let's talk at the end here about conflict detection and resolution, what's happening here. So I mentioned all objects have versions, and these are controlled by AppSync using these monotonic counters. The other thing important about this is when we want to detect conflict, we use a combination of the versions themselves with the client identities as they come in to detect if objects are in conflict, and we do an ANDing process on this on any of your authorization rules. And so this is important because even if you aren't in conflict from a version standpoint, you might not have authorization to update that item later as the rules change over time. And so this is applied to the individual rights as well. But we can use the GraphQL type information with these versions to do merge and reject decisions. So I'll talk about these in two pieces. The first is the simpler cases. So we have an optimistic concurrency control, which is, use common industry nomenclature is not exactly correct, something like last right wins or something. But OCC is actually, optimistic concurrency is the more correct control to use, which what that means is that the latest committed write with the correct version to the database is what's winning. Okay. And when the writes from multiple clients come in, we compare this against the database. And then, appropriately, we track this in the base and the delta tables, right? So if the version is wrong, data store on the client is actually going to get that response back from the backend and merge the correct item. And again, if the client had done a write here and the version was wrong, you don't lose the data on the client. It actually comes back in a callback for you as a developer to do something with. That's one option. Another option is when you do these writes, you can kick off a custom Lambda function. And in the AWS Lambda function, what we pass through is we pass in the version information, the old data, as well as the new data that's being tried to write. You get GraphQL type information. You also get the identity. But you as a developer in your custom Lambda, you don't have to do the versioning, right? So even though that information and context is there for you, AppSync, again, controls this versioning information as a centralized authority. You just have to say, okay, I've got this old data, this new data, the user that's trying to write it. What do I want to do? Maybe I want to just call a reject, or maybe I want to say, oh, the user is equal to, Richard or someone else. And if they are, now I want to resubmit the write to the system. And the versioning will go through the same flow of the process for detection on if the write should happen. The last one is maybe the most interesting here, and this is something called auto merge. Now, I showed you the GraphQL information, and if I take away the type from before, imagine you just look at the field specifically on the item being written, right? Your entity. And so let's say that your entity here is an item in DynamoDB, with AppSync in front of it. That's got three fields: name, age, and the breed of the dog, right? Now I've got two clients, and they're from their data store apps going to do a write, client A and client B. And on the first client, it's changing the age from 6 to 10. And on the second client, it's changing the breed to miniature schnauzer from Beagle. Now, what's going to happen here? Because if you look at just the objects themselves, you're clearly going to have some data loss. But because we've got the GraphQL type information, we can actually look at the different fields and compare them. And if we have non-conflicting types, we can union the results so that you get no data loss and we can merge the information. Now, what we do is we actually cascade down to the individual fields. So if we did actually have conflicting types, they would basically run that optimistic concurrency control on the individual fields to look at the last committed write of the database. So you don't get everything for free, but you actually do get some heuristics and some intelligence here to protect yourself from the basic union operations. This also works for lists as well. And this is lists in the terms of basic lists as well as sets if you want to perform these operations without any and dedupe automatically as well. So for example, in this case, I've added a new field, which is a list of the interests that Shaggy has. And I've got two other clients that want to update the interest with another record of cats and another one of dinner. This time when the writes happen, we're able to union that set. So it's a concatenation process that happens on the end based on the writes that happen from the clients. So with that, I want to stop here, and I appreciate everybody that's hung out for late nights. I'd encourage you to look more for this information on the Amplify site. That's docs.amplify.aws. We have a whole Discord channel as well that you can find for Amplify, that we've got a large amount of community that's participating every daily. And you can look at the getting started for JS for iOS or Android, anything there, as well as look at some more deep dive demos. So I will.
Hello, Denny. Denny. Denny.
Can you? I can't hear you.
Okay, so sorry. All right then. We'll slide into Slido, pun intended.
Oh, there we go.
And so we have no. Oh, we have one question. Where are the merge strategies performed? Mobile, client, or the backend?
They're performed at both. So the primary merge strategies that I outlined there they happen at the back end of the service. So it tries to go through those strategies depending on, and you can set them on an individual field in your GraphQL schema as well. So you could have some fields that are using auto merge, other stuff that's using Lambda, and even other stuff that's using optimistic concurrency. And then it passes the results to the client. If you want to on the client, though, you can also run a callback and do some extra client merging, including resubmitting the right to the backend if you wanted to do that. So you have control on both sides.
Great, and thank you for that answer. And we don't have a question, but Bogdan Kupkin is saying thank you very much. It's a lovely
No
message.
problem.
Okay, Richard, thank you very much. We'll wait a bit, a couple minutes, a couple seconds maybe. If there's another question, uh, thank you very much for your talk. And I just need to repeat that you're not going to be in the speaker's corner, correct? So if
Correct.
anybody from the audience or attendees are going to the 3D world or you watching from the 3D world, please note that Richard is not going to be in the speaker's corner, so don't be confused. Uh, yeah, I'm sorry, I'm hearing from another ear somebody else. Thank you. And I would just want to, I would like to thank you, Richard, and all the other speakers for the great talks today. One more apology for all the technical difficulties we had throughout the day. Again, it is our first MDev camp online, and some things are unpredictable, but we are doing the best we can. And I'm not sure if somebody from production is going to switch the screen. Maybe not. Never mind. I'm just gonna invite you all for tomorrow's day. Is gonna be full of session again. Please don't forget to go and visit our partners stands. Oh, and we have another question. I joined later, sorry. Anonymous said. So, Richard, there's a question for you. What will happen if you update some flat value, let's say string on both sides? Maybe you answered, but it was not here. I wasn't here. Will it get rejected?
Yeah, so if it's a scalar value, I think that's what we mean by flat value, but a scalar field, what will happen is if they don't conflict, they get the union of the results. And if they do conflict, one will win, and then the client that loses will get that returned back to them, and they can choose to resubmit or not. But we actually have one interesting thing on some of these rules. If you're interested in going a little bit deeper, the AppSync documentation has an entire page. If you just search for AWS AppSync documentation, you'll see a section of conflict resolution and detection. And we lay out the entire set of heuristics and rules there for you to walk through in detail.
Cool. Thank you. There was one last question, like last minute question, and now. Okay. Anything else you want to ask Richard before I wrap this up? I'll give you like last 10 seconds, maybe 5 seconds. Well, then please rate Richard's talk. It's on the Slido, and the rating is now open. Thank you very much again, Richard. Thank you for your time, for your talk, for your expertise, and sharing your knowledge. Thank you very much, all the attendees. Last but not least, or least but not last, I'm not sure how that's saying. I would like to thank you, our amazing partners, MSD, Microsoft, Bitrise, Kiwi.com, Showmax, TDC, Teleport, and JetBrains, and all the other partners, which there's a huge list on that. Please visit their stands tomorrow or today if you're still browsing in the 3D world. And we'll be looking forward tomorrow to see you again. Sleep well. Don't drink too much tonight. After party is going to be tomorrow, maybe online, maybe offline. It depends on you. And have a good night. And I'll see you tomorrow, guys.
Thank you.
Thank you, Richard.